In the last video, we introduced text classification and our simple classifier framework. Now we're going to talk about modeling for text classification. How do we assign a score to an XY pair using parameters W? For simplicity, we're going to focus on binary sentiment classification. So an input X is a sequence of words, typically a sentence or a document, and the classification label Y can be either positive or negative. Here are two examples of XY pairs from the Stanford Sentiment Tree Bank. The first type of score function we're going to consider in the course is a linear model. Here the parameters W are arranged in a single vector, so we're going to use our vector notation for W rather than the more general structured object notation we saw earlier. The score function is defined as the dot product between the parameter vector and a vector f of feature functions, which are computed for the XY pair. The rest of this video will be about ways of defining feature functions, often just called features, for text classification. Features have traditionally been an important part of NLP. Generally speaking, NLP datasets have inputs and outputs. Features are not included. You have to define them. Contrast this with standard machine learning benchmark datasets, like those in the UCI repository, which include fixed-length feature vectors for every instance. Engineering a good set of features has been a major interest of the NLP community over the past 25 years. However, feature engineering has been increasingly replaced by representation learning, which we can think of as learning features from data. We're going to do both in this course. In the literature on representation learning, features are often described negatively as costly, handcrafted, brittle, etc. But in practice, the simplest features usually account for most of the accuracy. And representation learning still has plenty of engineering and trial and error, so there's no silver bullet. Let's move on and start talking about features. Our starting point are Unigram binary features. A unigram is a word, and binary refers to the fact that the features return 0 or 1. Here are two examples. F1 returns the value 1 if Y is the label positive, and the text includes the word great, and 0 otherwise. F2 is similar, but only returns 1 if the label is negative. We usually think about features in terms of feature templates. So we'll define this Unigram binary feature template. To create features, this template gets instantiated for particular labels and words in our dataset. For an example training set with just two XY pairs and this single feature template, here are the actual features we would instantiate in the model based on the training data. And with each feature, we associate a weight. If we want to then classify a test instance x prime, given our features with associated weights and our choice of a linear model for the score function, we'll first use our model to score all possible labels for x, and then choose the label with the higher score. Even though we have 5 features in our model, only a couple of them have non-zero value for this instance. So the score of the positive label is W1, and the score of the negative label is W5. If W1 is bigger than W5, the classifier will return the positive label, otherwise the negative label. In that example, we saw another difference between a typical machine learning setting and NLP. The UCI datasets, for example, mostly have fixed-length dense feature vectors, with dimension ranging from a few hundred to a few thousand. In NLP, we define a small number of feature templates, but they're instantiated for potentially millions of feature functions. But then the feature vector for an instance is sparse, that is, mostly zeros, as we saw in the previous slide. Okay, back to these two features that were non-zero for our test instance. We're going to be learning these weights from data, as we'll see in the next few videos. But suppose we set W1 to be larger, and say we have no other features in the model, then on sentences in the training set with the word great, this classifier would have an accuracy of 69%. But great only appears in about 1% of sentences. And these are examples of ambiguity and variability in text classification. Great can mean many other things, and lots of other words can indicate positive sentiment. Here are some examples where great does not indicate positive sentiment. Could be due to negation, a different sense of the word, or multiple sentiments being present in the sentence, among other reasons. Many other types of features are in common use. One type is a unigram count feature. which returns the count of a particular word in the input text. Here's an example feature template for a count feature, which iterates through all words in X and counts the number of times a particular word appears, all for a specific label Y. Other common feature templates look at bigrams and trigrams, that is, 2-word and 3-word subsequences in the input. Instantiating these can very quickly lead to an unmanageably large set of features, especially for large training sets. This can lead to a problem where we have millions of features, but many of them only appear once in the entire training set. It's going to be hard to learn good weights for such rare features. One solution is to try using a feature count cutoff and only keep features that fire, that is, have non-zero value on at least k examples in the training data. You probably noticed that all of our features explicitly include an indicator function for the label being a particular value, like positive in this case. How about if we add a feature like this one that does not look at the label at all? Well, its weight doesn't end up mattering, because this feature function has the same value for all labels, and features with the same value for all labels will not affect the argmax in the classifier. So all of our features include the label explicitly. Defining features in this way may be different from what you're used to in machine learning. When using dense feature vectors in machine learning, the algorithm may automatically create weights for pairing every possible label with every feature. That is, you define a feature based on the input only, and then the ML code may create separate weights for that feature for every possible label. In NLP, we usually don't do things that way because it would lead to too many features. For example, consider part-of-speech tagging. There are 45 part-of-speech tags in the Penn tree bank, and we don't want to create features for all possible combinations of tags and words. This would be roughly 45 times the number of words in the vocabulary, and most words appear with just a couple of different part-of-speech tags in the data. So we tend to explicitly include the label in the feature definition, and only instantiate features that fire in the training data, possibly with a count cutoff.